Okay, so goal for today is to go through the WSF OS. That's the part of the Bluetooth stack that connects all the parts. As you can see on this all explaining graph, you can see the WSF box expanding over all of the other parts of it, of the stack. That's because WSF OS is the underlying infrastructure below all those parts. And that's what I want to go through today. So let's open up the project and let's go to the third party folder, Exactl, and here in the ws_core -core you will find, is it here? Yeah, I think it's here. Yeah, WSF. You will find the generic Ambiq, the generic versions of it, and slightly modified Ambiq one, which doesn't change that much, but you should probably link to those files in your makefile, the Ambiq modified ones. Okay, well then, what is WSF OS? Let's get through the actual source file, the main file, because I want to show you how it relates to the actual code we are using. So let's go to the main function. Let's find the dispatcher. So that's the function I mentioned in the previous video. This one dispatches the events to specific handlers. So if we go and find this function, yeah, as you can see, like I'm basically looking for a tag. It finds the tag in the Ambiq folder and the generic folder. Let's go into Ambiq one. At the bottom you'll see the path to it, and that's WSF_os.c file. WSF_os is basically a structure. It's basically a set of functions and a structure. First of all, there is the handlers array, and if we look at this tag, you can see that this is a callback function. So we've got an array of callbacks. That's how handlers are registered. And then there is the handler event mask. So those are the events that are registered for a specific handler. And if you look at this value, again, this is a generic implementation or Ambiq specific one. They probably don't differ. So that's basically uint8. It's a type def. So basically this is an array of uint8, because every event is basically a bit field. So you have uint8, and that's basically 8 bits that you can flip like switches for specific events. And there is a message queue, which also allows passing events to specific handlers. There is task event mask. This is also a type def for uint8, I think. Yeah, the same idea as this mask. So basically you can set several bits to signal to the OS what type of events need to be handled. And then there is the number of handlers. So that's a value that holds how many handlers are registered. And actually the number of handlers is limited by this macro. Yeah, this structure is wrapped in another structure. I don't know for what reason, but I guess there was a reason. I hope so, at least. I mean, looking at the name, it's like a task, so maybe you can implement multiple tasks. I don't know. There is, and in the end, this entire structure that we are interested in is instantiated through this structure here. So this is our actual OS, let's say. There's also this reference to FreeRTOS, but I'm not using this flag, this AM_FreeRTOS flag. I don't know exactly how FreeRTOS is used in this context, why it's there, and it's actually in the newer, as I mentioned before, in the newer version of Ambiq SDK, the FreeRTOS part is mandatory, I think, and that's why I'm not upgrading to the newer one. going back to the structure that defines the OS, let's see how it's modified and how it's read. When you want to register a new handler, you basically call the WSF OS set next handler function. You pass it the function which registers as a callback, and this function also increases the number of handlers to know how many handlers are registered, asserts that it's less than maximum handlers it can handle. Handler ID is basically the consecutive number. The first one will be 0, then another one will be 1, 2, etc. So that's how you just create new handlers. Going back to the OS structure, the next interesting part of it is this one. That's the collection of events for each handler. So if we, for example, want to check the events for a specific handler, we just use the same index as we used here. Let's go back to that function which registers the handlers, because the important part is that it returns that ID of the handler. So we have to keep track of that ID, and basically if we want to, for example, look up the events for the specific handler, we use the ID in this array to fetch the uint8 and basically check the bits in that uint8 to see which events are registered, which events are set to true, to 1 in this case, which basically means that if we want to set an event for a specific handler, there is a specific function for that, and that's WSF set event. So if we want to modify that part of the OS, we just specify a handler ID and a specific event. As you can see, the event gets set through OR operation, which means that a specific bit gets flipped on, basically using this event mask. Yeah, here the handler event mask for the specific handler ID is modified with that event, and task event mask gets the bit for WSF handler event gets flipped on, which basically means set a specific event for this specific handler, and also set a global status for the OS saying, hey, there is a handler event to be processed. But I will get there in a second. There's also this set a specific event. This is also in the same file, but this one, if you are not using FreeRTOS, like this one doesn't matter. There's nothing there except this block that's protected by this macro, FreeRTOS. I'll probably have to get into it later, but I didn't yet. So this, in my case, does nothing. Going back to this set event function, that's the last call, which for me, as I said, does nothing. Okay, yeah. So we went through the two first fields, setting new handlers and setting events for specific handlers. Then there is the message queue, which I'm going to talk about a bit later. And then there is the task event mask, that's the global state I just mentioned, that signals for the OS, hey, a specific type of event is to be handled. And for this one gets modified through WSF task set ready. And if you go to that function, you basically push a specific event which gets flipped in this field. Let's get back to the dispatcher function and see how it all comes together. Okay, let me maybe open another window. Let's make it bigger. So we can see the structure just next to the source code. Maybe let's make it a bit smaller. So the dispatcher function is actually the function which uses all the data stored in this structure and dispatches specific events to corresponding handlers. So first of all, it fetches that task, that global state function of the OS, so that would be this one. It fetches it here, creates a p task pointer, and that's where the actual processing of the event starts. So before I mentioned that there is this global state variable that signals to the OS what type of event should be handled, and there are three types of events for the OS to handle. That's the message queue event, timer event, and WSF handler event. First, let's look at the message queue event. That basically uses this message queue I mentioned before. This is basically a queue of structures that you can put elements in a queue and dequeue them later to fetch them. Let's not look into implementation of that. That's a bit too much. So handling events like that means that the OS dequeues a message from the message queue. So basically, as I mentioned before, ptask is a pointer to this state variable here, this structure. Oh, not this structure, this one. And uses this message queue. Checks if there is a message, if it's not null, and then pushes that message directly to a handler. Later I'm going to show you how a handler looks like and what that means. So it pushes 0 because the first argument would be the I think that's the event mask, yes, and pushes, since we are handling a message, we are just pushing 0 for an event and push a message. Actually, a message has an event mask in its side too, so it's just a different way of passing an event to a handler. Then the message gets freed. The next type of event is the WSF timer event. That's when a timer expires. In this while loop, we will go through all of the expired timers. And each expired timer holds, each timer holds a handler ID, because timers are actually binded to specific handlers. So we fetch that, we use that ID here to call correct handler through the actual OS state variable. We use the specific handler through the ID that's binded to the timer, and we call it with the message that's stored in a timer. That's how timers actually work. They hold a message with a specific event which gets passed to a handler. And the third type of an event for an OS is the WSF handler event. That's when a specific event gets set for a handler. So as I've mentioned before, if you go to WSF set event, that's the function that allows you to set a specific event for a specific handler. And as I mentioned before, those two lines, first of all, the first one sets a bit in a handler event mask for a specific handler, and then the global state turns on the handler event. So here the global state, if the global state has this handler event bit set, and then we use this handler event mask here, handler event mask. First it's fetched into a local variable, the handler event mask gets cleaned for that specific handler, and then the handler is called with this event mask. And that's 3 of the types of events that the OS can handle. So if we go back to the main file, we can see how it's actually used in practice. First of all, let's go to the exactl stack init function, which actually uses this pattern of setting new handlers a lot. Here we actually create like a generic handler ID local variable, which will be used later. I probably need to review those comments. probably might be out of date. First of all, there is also things like a memory pool set up for the OS, and that's something I'm gonna probably go into later. This setup of memory that I have used is probably like an overkill. It basically uses 4, 5, 6, 7, 8, 9, 10K in RAM, and it's probably an overkill. But the memory pool gets used in the background, and there is a ways to get an actual usage of it as a stats of how the memory is used, so it can be tuned down. So the memory buffer gets initiated, and that's it with the memory. Then the OS uses it as it needs to. The security modules get initialized. That's something that I basically copied. I think it needs to be there. I didn't get further into those parts of it yet. Yeah, here are the actual handlers set up. So as I mentioned before, in order to register a new handler, we call the set next handler, which takes the actual callback. So for HCI layer of the Bluetooth stack, so that would be this layer, we use this specific handler, which is defined in another file, and that returns us a handler ID, and we initialize that part of the stack with this handler ID. So basically this HCI handler is defined somewhere else. Maybe let's go there. Yeah, this one is, if you look at the bottom, is defined in HCI_main, and this pattern repeats that every handler we register is defined somewhere else. Then there is HCI driver handler. So those parts are basically copied from examples. I don't know if I would figure it out by myself which handlers need to be registered. So it is what it is. I just copied it. It works. Unfortunately, that's my big problem with this whole stack, with this whole setup, and that's a big part why I make those videos, is that it's very difficult to know what you need to know. The documentation doesn't exactly tell you what's expected of you to set up to make everything work. And unfortunately, the API doesn't map one-to-one with the Bluetooth stack. There are some other concepts introduced that wrap some ideas, some concepts from the Bluetooth stack. So it's not exactly easy to figure it all out. So for example, here you have L2C layer handler. So that would be this one. But that one also saves like a slave handler. Yeah, what is a slave handler? Not really sure. Why is it a slave? Okay. I guess it is what it is. Then we register the DM handler. That's a device manager, and actually those functions in this version of the SDK, they are only in a library, so you can't see their implementation. So for example, if I look for this one, for this tag, I can't really find it because it's basically implemented in a library. There is no source code for it in this version of the SDK. In the newer one, you can actually get through it, which is nice, but unfortunately I can't use it yet because I didn't port my setup to the newer SDK. And then there's a lot of other functions here, like connection init, connection slave init, security init, and some of those are actually described in this document. This is the modules part of the Cordio stack, and here you will see that it's the DM module, and the device manager module actually wraps the GAP idea, the GAP service of the Bluetooth. So if you go actually through this part, there's actually a lot of cool information here on this particular site. How pairing gets done and things like that. all of this, that messaging that gets passed through the WSFOS. So that's worth a read. But those, as I said before, a lot of those are just copied, and I hope that they should be there. And as I go, and if I see any problems, I'm gonna fix them. I'm gonna try to get more into that, but for now, a lot of those parts seem to work. Then the ATT service gets registered. Then the security module, and then we come to the application layer. So application also has a handler, and the HID application also has a handler. So that idea of an application is part of the actual stack. As you can see, here is the app framework, and that's something big in of itself. So I will get through it later. But what I also wanted to go through in this part is to go through setting up your own handler. Because basically, if you were to count all those handlers, I think it's 8 of them are registered here, and there is space for one more handler. So what I did is I inspired through one of the examples. I registered my own handler. So here, as you can see, button handler ID. I use my local function button handler. As you can see, it doesn't follow the proper naming convention, but a lot of things don't here, so that's something I need to clean up. So here you can see I'm still in the main file, and you can see the button handler function. It's got pretty long, so that needs refactoring, but this basically handles the key presses. If I press the button number 2, I set keyboard A button. That's like more of a test setup in a controller state variable that I have defined. And then later, and I set the send report to true. That's also a bit messy because it repeats again and again, so that this part of the code needs to be improved. But if it's set, then I push for the HID app part of it. I push the report, which means that I actually send the report of key presses to connected device. Okay, let's go back to registering the handler. So I'm registering this specific callback that spits out a new button handler ID. Assuming that's the last one, it will be probably number 8. This will be a value of 8. But I'll also use a timer. So this timer, which is also defined here in the global state, needs to have the handler ID set. So this value gets copied to the timer. There is also the power cycle timer, and this is also not, this is something that needs refactoring. I don't know if I necessarily need it right now in this way it's set up right now. So as you can see, both button timer and power cycle timer use the same handler. By setting the same handler ID, when those timers expire, this one or this one, they will both call the same function, button handler, because they use the same handler ID. So I also set event for the button handler with the power cycle timer event. I set this specific one, so as soon as we start, the power for the radio part of the device gets turned on. And for the buttons, set an event in a message of the timer. So when the timer, and I start the timer, and when the timer expires, it will handle this specific event. And then I call the dispatcher to, in a way, flash this setup. So before I get to the main while loop, this is already flashed, and I have turned on the BLE module, and I have started the timer, which as you will see in a second. Let's go to the actual handler. So button handler. So here I just, every time I handle a button timer event, so let's say a timer for the buttons expired, I have to restart that timer, because every time it expires it gets dequeued, which means that it gets deleted in a way. So every time it gets started, it expires, it needs to be created again. So here, as soon as it expired, I handled the event, the button timer event, through a message or through a direct event setup for this specific handler. So this first brackets, that would correspond to for the user to use WSF set event, because that's how you set the direct event. And the second parenthesis comes from actually handling the timer expiring. So if you go back to the OS dispatcher, yeah, here in the dispatcher, so we either go through here, since we handle a timer expiring, or we go through here, so a direct event set for a handler. So yeah, we set up a timer again. So the buttons are checked every, I think it's 10 milliseconds. So this actually, this block fires every 10 milliseconds. I think it's milliseconds. Yeah, start milliseconds, so I guess it should be. Yes, this block gets called every 10 milliseconds, and the buttons are checked through the HAL, in the end through the HAL libraries. Yeah, the state of the button gets fetched, and an actual mechanism of debouncing and all of that gets processed, and the state of the button gets fetched. So this specific button, that's the built-in button, this one doesn't do anything, but this, for example, sets a bit flag for left shift key pressed, and says, yeah, that there was a change in the state, so please send the report. Maybe I will just hold like a previous controller state and compare them, and then that way I can remove all of those, and then later, instead of checking send report, I can just compare those two states, previous and the current one, and then decide to send it. Don't know how I solve it yet, but that's not actually the important part. Okay, and then there is the power cycle event, and again, checking the direct event and checking the event in the message stored in the timer. So at the beginning I set the event was the direct event. Let me check, because I don't think it was. Yeah, so for the power cycle, yeah, we actually set the event directly. So button handler. So at the beginning I set the event directly, and then I flash those events, as in I handle them before going into the loop. And since I set the event, this will be true. This won't be because the event in the message isn't set, but this will be because I've set the event through the WSF set event, which means that it checks if the BLE is on, the Bluetooth itself is on. If it's on, then it actually turns it off, because the power cycle event, I don't know if it should be called power cycle timer event. The idea is that if you push that event, it will turn off or on the BLE, which means that at the beginning it checks if it's turned on. It's not, then actually it will go through the else block. So I think this code needs to be a bit refactored, because it's not easy to read what's going on here. But the idea is that at the beginning it will get here, and this part is interesting and important, that it actually turns on the radio, also does some other stuff, not necessarily sure what that is, but that one comes from an example too, and sets the global state, yeah, that the BLE is on. And that's it. That's how you implement a custom handler. As I've mentioned, this handler actually handles two situations. It's more of a, first it's this block to handle the power cycle timer event, and then there is this block, the one that handles the button timer event, and the same through the messages. So also what's important is that actually those variants or I think they are just macro. I think they are defined in the same file. Yeah. So here we are still in the main.c. As a global variable, you can see there is the button timer created and the button handler ID, which I used below, and power cycle timer also. I think this one doesn't get used at all. Power cycle timer. Yeah, it just gets binded to the same handler ID, but I never started because I don't see a reason right now. So I might just delete this timer. But anyway, the events themselves are also created here as defines. Maybe they should be variants of an enum. As you can see, the values are not overlapping, so they are not using the same bits of the uint8 value. Power cycle event would be, would it be this? 1, 2, 4, yeah. While while the button timer event would be, okay, this is not a good way to show that, but I hope you will see the idea behind it. So those use different bits. This is the power cycle bit that gets turned off or on, and that's the button timer event, which either gets turned on or off. So they can be set both at the same time. And they don't overlap, so there is no one gets mixed what's actually set. That's a long explanation for something very simple as a bit fields. So okay, I think that's it for the WSF OS. Yeah, next time I'm gonna go through the app layer and HID app layer. Those are basically copied from the examples and slightly modified. There is nothing very crazy about what's going on there. But I think that might be the last piece of the stack puzzle that's important for explaining. Other parts I haven't even touched that much. The gap part is interesting because that's how you advertise your device. It wraps all of those ideas of advertising, connecting, bonding, and things like that, while the GATT profiles is how all of the data that the connected device, your PC, can fetch. So those two ideas, those two parts of the stack are very important, and they are pretty important to understand, at least in a basic sense. I'm not sure if I'm gonna go through them, but yeah, I think that's enough for now. Thanks.